Welcome to a series of lecture series on mathematical matrix applications. So, in the last lectures we have seen about Laplace transform, their property, inverse Laplace transform, various functions, how to find their Laplace inverse and Laplace transform, etc. So, now we will see applications of Laplace transforms. What are the various applications of Laplace transforms? So, Laplace transform can be used in solving various ordered differential equations which we faced in various engineering problems like in engineering like electrical engineering problems or in mechanical engineering problems. We face some ordered differential equations or partial differential equations which can be solved using Laplace transforms. Some integral equations, some involving discontinuous functions which can be solved using Laplace transforms. So, let us see the application of Laplace transform part 1. So, the first problem is the differential equation for a current I in an electrical circuit containing an inductance L and a resistance R in series and acted on by an electromotive force given by E sin omega t satisfies the differential equation this. So, what is the differential equation? It is dL di by dt plus Ri is equals to E sin omega t. E sin omega t is the EMF, electric motive force. Okay. So, we have to find out the value of the current at any time t if initially there is no current in the circuit, that is it is given to us at I at 0 is 0, that is I at t equal to 0 is 0, it is given to us. So, how to solve? So, we can solve this problem using our differential equations techniques also, but we can solve the same problem using Laplace transforms also. So, how can we solve this using Laplace transform? Let us see. So, you first take Laplace both the sides. Okay. So, this L is inductance. So, L into Laplace transform of di by dt plus R is constant, Laplace transform of I is equals to E is constant, Laplace transform of sin omega t. So, it is L. Okay. Laplace transform of di by dt. We already know that Laplace transform of f dash t is what? F dash t is nothing but p f p minus f 0, where f p is Laplace transform of f t. Okay. Now, here f t is here it is I dash t di by dt, it is I dash derivative of I respect to t. So, what the Laplace transform of this using that expression is will be, it is p f p minus f 0, f 0 means I 0 plus R into, suppose Laplace transform of I is f p, okay, which is equals to E and sin omega t is omega upon p square plus omega square. So, I am assuming Laplace transform of I as f p, you can call it some other function also f p. So, it is p into Laplace transform of I which I am calling as f p minus I 0 or f 0 plus R into Laplace transform of I which I am calling as f p equal to E into Laplace transform sin omega t, it is omega upon p square plus omega square. Now, I 0 is 0 is given to us. Okay. So, you can collect f p. So, f p will be nothing but L p plus R, it is 0 and it is E omega upon p square plus omega square. So, from here f p is nothing but E omega upon p square plus omega square into L p plus R. So, what will be this is f p and f p is nothing but Laplace transform of I. So, what will be I? Basically, I is nothing but function of t. Okay, I is equal to I of t. I is nothing but function of t here. So, this implies I t will be nothing but Laplace inverse of E omega upon P square plus omega square into Lp plus R. So, now to find out the solution of this differential equation IT, we have to find out the Laplace inverse of this expression. This is the only thing left now. Okay. So, how can you find out Laplace inverse of this? So, let us focus on the Laplace inverse now, Laplace inverse of this expression. So, this Fp is what? Is E omega. E omega is constant free from P, it is P square omega square into Lp plus R. So, one way is you can make partial fractions or you can use convolution theorem. So, we can make partial fraction as well. So, it is AP plus B upon P square plus omega square and plus C upon Lp plus R. So, E omega will be nothing but AP plus B. We can find out A, B and C. Now, compare the coefficient both the sides. P coefficient of P square here is 0 and here it is A L plus C, coefficient of P square. Now, coefficient of P, suppose coefficient of P will be nothing but it is A R plus B L and here it is nothing, so it is 0 and constant quantity is B R plus C omega square, which is E omega. So, using these three expressions we can easily find out the value of A, B and C. When we substitute these values over here and take the Laplace inverse both the sides, so we can find out what will be IT. IT can we find out? Okay. So, what will be IT? IT will be nothing but Laplace inverse of this expression means this expression. So, this Laplace inverse of this will be nothing but A into cos omega t plus B upon omega sin omega t plus C upon L, we can take out common, which is nothing but e ki power minus R by L times t. Okay. So, these ABC can you find out using these three expressions, using these three equations. So, we can substitute the values of ABC from these three equations over here, which will give us the value of IT, function IT. Okay. Now, see the next problem. Again it is a electrical circuit problem. In an electrical circuit with EMF ET, resistance R and inductance L, the current I builds up at a rate given by this equation. Okay. Now, here if the switch is connected at t equal to 0 and disconnected at t equal to A, find the current I at any time t. Okay. So, how can we proceed for this problem? So, what is the governing equation here? I di by dt plus Ri equals to Et. Okay. The same equation, it is LCR circuit equation, I mean EMF, resistance and inductance. This is the equation given by differential equation given by this expression. Now, it is given that a switch is connected at t equal to 0 and disconnected at t equal to A. What does it mean? That electromotive force, which is Et, it is some constant quantity, say E, when t varying from 0 to A, and disconnected at t equal to A means it is 0 when t is greater than or equal to A. So, this is how electromotive force works for this particular problem. Okay. Now, to find I at an instant t, we will use Laplace transforms. So, it is take Laplace transform both the side, it is L, it is again Laplace transform of di by dt, which is given by P into Fp minus I0 plus r into Fp is equal to Et. Et is nothing but this expression, given by this expression. So, it is 0 to infinity, because we have to find out Laplace transform Et. So, Laplace transform Et is nothing but 0 to infinity Et into e power minus Pt dt, and it is nothing but 0 to a e power minus Pt dt, otherwise it is 0. So, which is equal to e power minus Pt upon minus p 0 to a, and which is equals to minus e by p e power minus ap minus 1. So, this is the right hand side, and what is Fp? Fp is nothing but Laplace transform of It. This I am assuming here. Okay. Now, we assume that at t equal to 0, initially there is no current in the circuit, so I0 is 0. Okay. So, I0 is 0. So, this implies basically Fp PL plus R is equals to E upon P 1 minus e power minus AP. Because I0 is 0, initially I am assuming that there is no current in the circuit, it is 0. Fp is LP plus R, and right hand side is E by P 1 minus e power minus AP. Now, the only thing is find It, which is nothing but Laplace inverse of Fp, and Fp from here is nothing but Laplace inverse of E by P into PL plus R 1 minus e power minus AP. So, now we have to find out the Laplace inverse of this expression. This is the only problem left now. So, how to find Laplace inverse of this? Now, again, what is Fp? Fp is E upon P into PL plus R minus E into e power minus AP upon P into PL plus R. This is Fp, and we have to find out Laplace inverse of this Fp. Okay. So, first let us find the partial fraction of this expression. So, this is partial fraction can you find out when you put this equal to 0. So, this is Rp plus when you put equal to this, so it is minus L by R into PL plus R. So, you can check when you take the LCM, you can get the right hand side. So, these are the partial fraction of this expression. So, what will be Fp now? It is E upon Rp minus E into e power minus AP upon Rp minus plus E into e power minus AP Now, the Laplace inverse, that is It, will be Laplace inverse of Fp. So, this will be the Laplace transform of this expression. So, we can further divide it into 2 when t is more than a. So, it is 1. So, it is 1, it is 1. So, that will give the It when t is greater than a, and when t is less than a and greater than 0, it is 0, it is 0. So, that we give gives the value of It when t is lying between 0 and a. Okay. So, this will be the It for this expression. So, this is how we can solve some problems using Laplace transforms. Now, we will see some more problems which can be solved using Laplace transforms. Okay. These are simple problems just to illustrate how can we use Laplace transform to solve ordinary differential equations. So, the problem is simple, it is y double dash minus 6 y dash plus 5 y is equal to e to the power 2 t, and y 0 is 1 and y dash 0 is also 1, it is given. Okay, it is 1 minus 1. So, it is 1, y 0 is 1 and y dash 0 is minus 1. Okay. So, now how to solve this problem using Laplace transforms. So, first take Laplace transform both the sides. Okay. So, it will be Laplace transform y double dash minus 6 times Laplace transform of y dash plus 5 times Laplace transform of y is equals to Laplace transform of e to the power 2 t. Now, from the Laplace transform derivatives we know that the Laplace transform y double dash is nothing but p square f p minus p f 0 minus f dash 0. You call it f 0 or you can call it y 0, there is no problem, because here instead of f we are having y. Okay. So, minus 6 and Laplace of y dash will be nothing but p f p minus y 0 plus 5 times Laplace of, okay, Laplace of y is f p and it is nothing but 1 upon p minus 2. Laplace of y I am calling as f p. So, y 0 is 1 and y dash 0 is minus 1, it is given. So, f p will be, it is p square minus 6 p plus 5 and y 0 is 1, so it is minus p minus minus plus 1 and it is minus minus plus 6 into 1 is 6 is equals to 1 upon p minus 2. Okay. It is 1, it is minus 1, so it is p, it is plus 1 minus minus plus 6 into 1 is 1. So, f p will be nothing but 1 upon p minus 2 into p square minus 6 p plus 5 and it is, this will go to that side. So, it is plus p minus 5 or 7. Okay. 6 plus 1 is 7. So, it is p minus 7 upon p square minus 6 p plus 5. So, it is nothing but 1 upon p minus 2 into, it is nothing but 5 and 1. So, that is p minus 1 into p minus 5 plus it is p minus 7 upon p minus 1 into p minus 5. Now, what will be y t? Y t will be nothing but Laplace inverse of f p. So, Laplace inverse of this can be find out using partial fractions. Okay. So, you can use partial fractions to find out the Laplace inverse of this. So, that will give the final answer of final expression for y t. Okay. Now, we will see the next problem involving t also in the y double dash or y. Let us solve this problem. So, this problem can be completed. Okay. You take the partial fractions, make the partial fractions and then take the Laplace inverse of these expressions. Now, next problem t y double dash plus 2 y dash plus t y equal to 0, and it is given to you that t y at 0 is 1 and y at pi is some value 0. Okay. Okay, this is given to you. Now, how to solve this problem? Again you will use Laplace transforms. You take Laplace transform both the sides. So, Laplace transform of t y double dash plus 2 times Laplace transform of y dash plus Laplace transform of t y dash t y equal to 0. Now, what is Laplace transform y double dash? I mean f double dash, okay, f double dash t is nothing but p square f p minus p f 0 minus f dash 0, and Laplace transform of t f double dash will be what? Will be nothing but minus 1 ki power 1 d by dp of Laplace transform of f double dash t by the property of multiplication with t. Okay. So, now Laplace transform of t into y double dash will be what? Will be minus 1 ki power 1 d by dp of Laplace transform of y double dash. So, Laplace transform of y double dash is p square f p minus p into y 0 minus y dash 0 plus 2 into Laplace transform y dash. Laplace transform y dash is nothing but p f p minus y 0 plus Laplace transform of t into y dash again is nothing but minus 1 ki power 1 d by dp of Laplace transform of y, which is f p, that is equal to 0. Because I am assuming the Laplace transform of y t as f p. Now, let us simplify this. It is minus derivative with respect to p, so it is p square into f dash p plus f p into 2 p minus derivative with respect to p is y 0 is 1 and derivative this is 0 plus 2 p f p and y 0 is 1 to minus 2 minus f dash p is equal to 0. Okay. It is 2 f p, 2 p f p, y 0 is 1, so 2 into 1 is 2. Okay. Now, it is nothing but this implies f dash p into minus p square minus 1 with f p what we will be having. Now, it is minus this and plus this, so both will cancel out. Okay. It is minus minus plus 1 minus 2, so it is minus 1 equal to 0. So, what will be f dash p? F dash p will be nothing but 1 upon negative p square plus 1. So, what will be f p? You integrate both sides, f p will be nothing but minus tan inverse p plus c. Now, now you find Laplace inverse both the sides to find out y t. Okay. So, so y t will be nothing but this implies, so it is f dash p minus p square minus 1, it is minus, okay, it is minus minus plus 1, okay, it is minus minus plus 1, okay, plus 1 minus 2 is minus 1, okay, and it is 1 upon p square plus 1 and p square plus 1 is tan inverse p plus c. Okay. Now, to calculate this c, we will use corollary of existence theorem for Laplace transforms. We know that as p tend to infinity, f p must tend to 0. So, take p tend to infinity both the sides. So, p tend to infinity. So, at p tend to infinity, limit p tend to infinity f p must be 0. So, this is 0 equal to minus tan inverse pi by 2 tan inverse infinity, okay, plus c. So, this implies c is pi by 2. So, f p is nothing but minus tan inverse p plus pi by 2 and pi by 2 minus tan inverse p is nothing but cot inverse p. So, now we have to find out Laplace inverse of this Fp. Okay. So, take the derivative both the sides, or we can take Laplace inverse here itself. If we take the Laplace inverse here, so it is nothing but minus t Ft, and it is nothing but minus of sin t. So, Ft will be nothing but sin t by t. If you take the Laplace inverse here itself, we can proceed from here also. From here to take the, if you want to find out the Laplace inverse of Fp, again we have to differentiate it. So, we will go back to the same expression. Okay. Then the Laplace inverse of this will be nothing but sin t upon t. So, this is nothing but yt. Now, y at pi must be 0 which is satisfied, y at pi is 0, so which is satisfied. So, hence this is the expression, their solution for this problem. Now, similarly these problems can be solved using Laplace transforms. Whenever we involved with unit step function or delta function right hand side, so such problems can also be solved using Laplace transforms. Okay. You take Laplace transform both the sides and then take the Laplace inverse, that will give you the final answer of the same problems. So, thank you.